Hi, so I'm going to talk about my favorite and most technically challenging project that I've worked on. This is the development of a Unix-like operating system. So I did this project about a year and a half ago. The whole code base is about 50,000 lines code, give or take. So just a quick introduction, what is an operating system? Well, operating systems are software that manage hardware resources, so the actual computer processor. What the OS does is it provides a platform or an abstraction on which applications can be built. So examples of services it provides are memory allocation for multiple programs, scheduling of processes, and providing access to I/O functionality, such as your mouse, keyboard, or the display screen. So you can think of the operating system almost as an API for the computer itself, for whatever program you're building, whether it's a text editor, or a web browser, or Skype, or Paint, or anything like that. Alright, so in my project I implemented the following functionality. It breaks down into three main components. Number one, there's thread synchronization using primitives such as locks, semaphores, and condition variables. Next, there were system call implementations of fork and execv for creating new programs or processes. And finally, there's virtual memory or address space management. So in this video, I'm going to focus on the thread synchronization and explain some of those concepts and show the code that I used to implement it. Alright, so what is a thread? Just briefly, a thread is a collection of code or a stream of instructions. Obviously, every program needs to have at least one thread. At any given time, your computer runs dozens to hundreds of threads at once. Just hit Control-Alt-Delete and go to your task manager, for example. So the operating system does this by using a timer, say 10 milliseconds, to trigger a context switch. And what this does is it changes which thread the CPU processor runs. So you can only run per CPU processor. Let's say, for the purposes of this project, it was on a uniprocessor MIPS system, so only one CPU. And obviously one computer can only run one set of instructions at a time. It's got to run, instruction 1, then instruction 2 serially. So what context switches allow you to do is to switch every 10 milliseconds between threads. So it gives the user kind of the appearance of running multiple programs at once, but really all you're doing is switching them in and out. And the way this is implemented, you could have a hardware timer interrupt every 10 milliseconds, and then that would trigger the loading of a new thread. So thread synchronization means having cooperation between threads to ensure a consistent program result that's independent of the ordering of thread execution. So ordering in this case means scheduling, what order the threads are run, swapped out, and swapped back in. So we use three main data structures that help us do this. There are locks, semaphores, and condition variables. So I'm going to start by explaining each of those and then showing the code. Here are locks. So let's have an example problem to see why these might be useful. You have two threads and they're both running code that represents withdrawing money from a bank account. So you have a withdrawal amount, you have a current balance, bank account.get balance. And then what you do, you check if your withdrawal amount is less than the current balance, and if it is, you set the balance to the new updated balance, and then you return the amount that you withdrew. So what are some problems if multiple threads, or if multiple users, let's say, are trying to run this code at the same time? They're trying to do this process all at once. So the first thing to notice is that the bank account is a shared data structure. So let's say your bank account.get balance returns 5,000. And now let's say both threads run to the point of this green arrow right here. So both threads have local variables current balance, which tell them that their bank account has $5,000 in it. Now let's say the scheduler picks thread A to run, and thread A goes through the next three lines of code, which withdraw the money and update the bank account. Well, is the condition true for thread A? Yeah, sure, everything works out fine here. We update the balance to 5,000 minus 4,500, and we return the withdrawal amount. Now, there's a bit of a problem when thread B runs right after this green part. So it's going to come in, it's going to do this if condition using its local variables, but current balance, according to it, is still $5,000, even though in real life, thread A just ran and took out 4,500. So the current balance should actually be 500. but according to thread B, it's 5,000. So what ends up happening here is that both threads can take out $4,500, yet the system only thinks that one withdrawal occurred because the current balance will be set to 500 twice. So it would be great if ATMs worked like this in real life for us, but not so much for the banks. And we're going to use the data structure locks to solve this synchronization problem. So what we have here is what we call a critical section. It's a section of code where you only want one thread to run it at once because you have sensitive shared variables, in this case the bank account. So to fix this, what we do is we wrap around the critical section lock acquire and lock release. And the idea is that between these two lines of code, whatever's in between can only be run by one thread at once. So the semantics of this is that whichever thread runs lock acquire first will get to run the critical section, but then another thread that comes in after the first thread has acquired the lock will go to sleep. And what that means for a thread going to sleep is that the scheduler moves the thread not in the running queue, but in the sleeping queue. And threads in the sleeping queue don't get swapped in during context switch to the processor. So this creates mutual exclusion, and we have complete atomicity around our bank account shared variable. Okay, so let's go to some of the code that shows how this works. First of all, when we create our lock data structure is very simple. It's got a name for debugging purposes, but what's important is that it has a thread member. Lock this thread, and that represents which thread has the lock. So we go to lock acquire. Okay, so first kind of redundant case, if we already hold the lock, just return, don't do anything, we're fine. Then what's important is we turn off interrupts, and while the lock is taken, while we don't have the lock, while this thread member is not null, what we do is we actually go to sleep on the lock. So that's the case I was talking about, where if you're the second guy to come in here and somebody else has the lock, you get to go to sleep. Now it's important to turn off interrupts in our uniprocessor system. Yeah, by the way, this project was done on a uniprocessor MIPS system. So if you really want the real atomicity, you use interrupts to ensure that these operating system dependent parts of the code are only run by one thread at once. So anyways, you turn off interrupts, you go to sleep. Thread sleep requires interrupts to be off so you don't mess up the context switch. Like I said, you don't want to interrupt the kernel while it's changing program states. Anyways, eventually what happens is other threads release the lock, they finish running the critical section, and then you get to acquire the lock by setting the lock's this thread member to the current thread, which is the thread running this code. And then of course you turn interrupts back on. So that's lock acquire. Lock release is pretty simple. All it needs to do is turn off interrupts, and if you have the lock, you just set this thread member of the lock to null. And that's the condition check we use to see if anyone else has it. And then we turn interrupts back on and we go about our business. Similar to small member lock do I hold, it just checks if lock this thread member is equal to the current thread. Okay, so that's locks in a nutshell. Moving on here, we have condition variables. There we go. Oh wait, sorry, no, I want to talk about semaphores quickly. So semaphores are very similar to locks, except you have a multi-count. So instead of mutual exclusion, where only one thread can run the critical section, you can have a limit of, say, 10 threads running the critical section. And an example of where this would be useful is, let's say you have a network buffer, and you want to limit the number of write requests to manage your bandwidth and not overrun the system. So semaphore create, it's very similar to the lock, except instead of just looking at lock this thread being null or not null, we look at the semaphore count variable. So semaphores have two operations. It's not acquire and release, they're called P and V for historical reasons. Some Dutch guy came up with it, I guess. And P represents taking one of those resources. So similar mechanics to locks, how we sleep with interrupts off if the count is 0, but if it's not, what we do is we decrease the count because that's representing us taking one of these semaphore resources. So us taking one of the spots in the network buffer in that example I was just talking about. And V is the analog to that. So we release a resource just by increasing the count. Okay, now we can go to condition variables. So, wait, this is the wrong slide. 1 second. All right, so condition variables, I like to use the phrase wait until I signal to describe what they do. And the example I'll use is this. You have two threads. One of them is initializing a variable, and the other one is using that variable. So clearly from this example, you can see there's a problem if thread B goes first. I mean, it's going to try to make withdrawal on bank account X, but if X doesn't exist, then this is obviously going to crash. So what do we do in this case? We use something called condition variables to make sure that our ordering is correct. So to more formally define condition variables, they're an ordering mechanism that have threads wait before they execute any more code, only after a certain condition has been met. So in this case, thread A has the condition that, so thread A is signaling the condition of X being initialized before thread B can run. So these are the semantics. Let's say thread B gets ran first. Condition variables are used in tandem with locks. So thread B acquires a lock and then it waits on a condition variable with that lock. And basically it's sleeping until thread A gets to run and it gets to signal on that condition variable. The other option besides signaling is broadcasting, which would wake up all threads waiting on the condition variable, because you can have multiple threads waiting on the CV. Signal is just for one thread. So yeah, one interesting part of the mechanics, it's combined with a lock, because initially the lock was designed to protect the condition variable itself. The condition variable in this case is X. The existence of X is the condition. And similar to the previous example, X is going to be like a sensitive shared variable, which is why having a lock surrounding it is very useful as well. Okay, and let's go through that code. All right, condition variable structure. Really not too much special going on in here. All right, the wait function. So what we do is we turn off interrupts. Then if we hold the lock, what we do is we release it and go to sleep. So as you see in the mechanics, we acquire the lock, and then in CB wait, we're actually releasing this lock, and then we're sleeping on the condition variable. So just a little bit more about the lock. The alternative is that without the lock, once the threads are woken up by the CV signal call, they're going to engage in kind of this unordered free-for-all in which they all try to use the condition variable, which in this case is X, the existence of X. While we could have done locking separately around X, like instead of having lock acquire here, we could just have lock acquire around the make withdrawal call. It's just become convention in the Unix POSIX threads that you do it this way, just based on common use cases, I take it. So I have some variations that I created that I found useful later on in this project. This function is CVWaitThread, and instead of sleeping on the condition variable, I would just put to sleep whatever thread I passed in. All right, and let's go over the signal code. Signal is very simple. All you're doing is you're waking up whichever thread was sleeping on that condition variable. So in our example, once thread A does signal, all it's doing is telling the scheduler to move thread B from the sleeping queue back to the running queue. So now thread B can continue running the code and make the bank withdrawal. Again, I have some variations on this. Broadcast is the main variation, where instead of waking up a single thread like in signal, you wake up all threads sleeping on the condition variable. And I think that was about it that I wanted to cover in this video. It's kind of late, and explaining any more would probably take quite a bit more time. So thanks for listening. That's a bit of the thread synchronization work I did in this project.